Let me tell you about the most common wall in LLM deployment. A team fine-tunes a 7 billion model on a big 80 gig GPU. Works perfectly. They ship it to a partner on a smaller 24 gig card. The partner hits load. The process crashes instantly. The checkpoint is 28 gigabytes. The card has 24. Nothing fits. The fix is quantization, and the idea is almost insultingly simple. Store each weight in fewer bits, so the whole model compresses into the memory you actually have. And you can derive the math yourself. Every weight is a number, and the bits used to store it is the precision. Memory is just parameters times bytes per parameter. Full precision, 4 bytes a weight. Half precision, 2. NT8, 1 byte. NT4, half a byte. That's the whole table. So watch our 7 billion model shrink. At full precision, 28 gigs. Half precision, 14. NT8, 7. NT4, just 3.5. INT4 cuts memory eightfold. A model that demanded a $10,000 GPU now runs on a $500 one. That's the whole pitch in one number. But why does it work? Why don't the rounding errors wreck the model? Here's the beautiful part. Weights are static, computed once in training, then frozen, representing smooth, slowly varying features. Round them down and the small errors spread across billions of values and largely cancel out. Activations are the opposite. Intermediate results computed fresh every forward pass, spiking to wild values depending on the input. Quantize those aggressively and quality breaks. So most schemes quantize only the weights, keeping activations full at runtime. Now the misconception almost everyone holds. People think NT4 means 4-bit math everywhere. It does not. Weights are stored in 4 bits to save memory, but the GPU dequantizes them back to half precision before every matrix multiply. You save memory and bandwidth. You don't do arithmetic in 4 bits. And that's exactly why it's faster. On modern hardware, the bottleneck is loading weights from memory, not the compute. Smaller weights, less to load, faster inference. Now the 4 formats you'll meet: GPTQ, which first brought NT4 to LLMs without catastrophe. It quantizes layer by layer using a small calibration dataset to minimize each layer's error. Works on any GPU. AWQ, activation-aware. It spots the salient weights, the ones multiplied by big activations, and protects them from aggressive rounding. Often matches or beats GPTQ with a simpler calibration. GGUF, the format for llama.cpp and ollama, offering a family of levels and running on CPU when you have no GPU at all. And bitsandbytes, quantizing on the fly in Python. Convenient for experiments, slower at inference than the rest. There's also a split worth naming. Post-training quantization just compresses a finished model using a few hundred sample prompts. Fast, no cluster. GPTQ, AWQ, bitsandbytes, all live here. Quantization-aware training is fancier. It bakes the precision loss into training, so the model learns to work around it. More aggressive compression, less drop, but you have to retrain. For most people, post-training is plenty. So what does it cost in quality? NT8 is almost always safe. Across the major families, less than 1 point on standard benchmarks. Indistinguishable from full precisions. NT4 costs more, typically 2 to 5 points on reasoning and knowledge tasks. But here's a gorgeous fact. Bigger models tolerate it better. A 70 billion in NT4 often beats a 7 billion in FP16 on both quality and memory. Go below NT4 into 3 or 2 bits and quality falls off a cliff, not for general use. So that's the trade, clean and honest. You spend a few points of accuracy, you buy back the memory that decides whether your model runs at all. And most of the time, on a card that was 3 gigabytes too small, that's the best deal in all of deployment.